You see it everywhere, right? On your stereo, on a microphone spec sheet, the decibel. But what does it actually mean? Honestly, it's one of the most common and probably one of the most misunderstood units of measurement out there. So let's dive in and finally get this thing sorted out.
Right. Get your head around this for a second. The quietest whisper you can imagine has 1/1,000,000th the power of a jet engine. That's the core problem the decibel was invented to solve. The range of sound our ears can handle is just, well, it's immense. A simple linear scale, like a ruler, would be completely useless. You'd need a measuring tape that stretches for millions of miles just to chart the difference between a pin drop and a rocket launch. So how on earth did they crack this problem way back in the 1920s?
Well, the whole story starts with the telephone. You see, the early engineers over at Bell Telephone Laboratories needed a really practical way to figure out how much signal they were losing over those long copper cables. But, and this is the key part, they needed a scale that actually matched how our ears perceive changes in loudness. It had to be human-centric.
So, in 1924, they came up with something called the transmission unit, or TU. And what's so cool about this is its purpose. It wasn't just some abstract measurement. 1 TU was designed to be the smallest change in volume that an average person could actually detect. It was literally built around us. A few years later, they renamed it the Bell to honor the one and only Alexander Graham Bell. But the Bell turned out to be a little chunky, a bit too broad for everyday work. So they did something simple. They just divided it by 10, and voila, the decibel was born. And that simple tweak gave us the perfect, fine-tuned unit for mirroring our hearing.
So what is this magic trick that mirrors our hearing and tames these gigantic numbers? The answer, the big aha moment, is the logarithm. Instead of trying to multiply these huge, unwieldy values, logarithms let us turn it all into simple addition. It's a way to compress these vast, mind-boggling scales into something we can actually work with.
And this slide just lays it out so perfectly. Check it out. On the left, you've got the linear scale. That's like trying to measure the universe with a tangled-up tape measure. The numbers just explode. But on the right, that's the decibel scale. It's like a neat, simple, pocket-sized ruler. That same enormous range gets compressed into these easy, manageable numbers. A billion-fold increase in power becomes a simple jump from 0 to 90 dB. It's just so elegant.
Okay, let's just peek at the math, but I promise it's way simpler than it looks. For things like electrical power or sound intensity, the formula is 10 times the log of the ratio between two values. So let's break that down. If you increase your power by 10 times, well, the log of 10 is just 1. Multiply that by 10, and you get a plus 10 dB change. Easy. What if you increase the power 100 times? The log of 100 is 2. Multiply that by 10, and that's a plus 20 dB change. See how it works? We're just turning this wild exponential growth into simple, linear steps.
But then, you see this other formula with a 20 instead of a 10. And this is for stuff like voltage or sound pressure. So why the change? It all comes down to a super simple rule in physics. Power is proportional to the voltage squared. And when you're using logarithms, that little squared exponent gets to come out to the front and multiply the 10, which gives us 20. The most important thing to remember is this. Even though the formulas look a bit different, they're both designed to make sure a decibel always represents the exact same change in power. It's what keeps the whole system consistent and reliable.
Now this next part is absolutely crucial. This is where most people get tripped up. Just saying something is 20 dB is totally meaningless on its own. It's just a ratio, a comparison. You have to ask, 20 dB stronger than what? And this is why decibels come in two main flavors, relative and absolute. First up, we've got relative decibels. This is when you just see dB with nothing after it. It's all about describing a change or a comparison. So if you hear that an amplifier gives you plus 20 dB of gain, it's just telling you that the output voltage is 10 times stronger than whatever the input voltage was. It's a ratio that lives inside the system. But if you want to measure a specific, concrete level, something you can compare with anything else in the world, you need an absolute decibel. And this is where you see those little suffixes pop up, like dBm or dBSPL. That little letter at the end is the secret sauce. It anchors the measurement to a fixed, universally agreed upon reference point. It turns a floating ratio into a solid, absolute value.
And here are the most common ones you're going to see out in the wild. You got dBm, that's referenced to 1 milliwatt. You'll see that in pro audio and telecom power. dBSPL, that's for sound pressure level, and its reference is the quietest sound a human can possibly hear.
Then there's dBFS, which stands for full scale. That's for digital audio, where the reference is the absolute maximum level the system can handle before it clips. And dBu is a common voltage standard in pro audio. See? Each little suffix gives the decibel a concrete, real-world meaning.
Okay, that's enough with the theory. How can you actually use this in the real world? Let's get into some practical rules of thumb that'll make you feel like you've been using decibels your whole life.
Seriously, if you just memorize these, you are golden. A change of plus 3 dB means you've doubled the power. Easy. A change of plus 10 dB, you've multiplied the power by 10. And because of that other formula we saw, a plus 6 dB change means you've doubled the voltage or the sound pressure. These are just fantastic mental shortcuts to have in your back pocket.
All right, let's bust a couple of huge myths. First, 0 dB does not mean silence. Nope, it simply means your signal is at the exact same level as the reference value. So 0 dB SPL is just the quietest sound we can hear, not the absence of all sound. And second, you can't just add decibels together. If you have two speakers and they're each putting out 60 dB SPL, you do not get 120 dB SPL. Remember our rule? You're doubling the power, which is a 3 dB increase. So the result is actually around 63 dB SPL.
So think about it. After almost 100 years, why is this unit, something born from old-school telephone lines, still so incredibly fundamental to pretty much all of our modern technology? It really all comes down to three brilliant ideas working together. 1. It tames these absolutely massive ranges of numbers and makes them easy to handle. 2. It's perfectly aligned with the way our own senses, our own ears, actually work. And 3. It simplifies the math in a huge way, turning complex multiplication into simple addition, which for engineers is an absolute game changer.
And that's really the heart of it. The decibel isn't just some random arbitrary unit somebody made up. Its lasting power comes from being this perfect blend of elegant math, fundamental physics, and human biology. It's a testament to solving a problem by getting a really deep understanding of its true nature.
So in the end, the decibel is so much more than just a way to measure loudness. It's a powerful way of thinking about ratios and scale that has proven itself time and time again for a solid century. From sound and electronics to communications and way beyond, its job is to make the impossibly large understandable. The only question left is, where are we going to apply this incredibly elegant tool next?